So this is a video about fracture toughness in homemade composite materials. So I'll be taking some household materials, water, newspaper, soap, and some carbonated water, and making various composite materials from that, and testing their toughness by dropping a known mass on them. So I'll start off with just frozen water, just as a control, and drop a sledgehammer, I guess, one of the easiest things I found, from a known height, about 3 feet, and I weighed its mass. And so here we have some Mathematica code, just some quick, dirty calculations of the energy it has before it impacts the material, the impact velocity, and the impact momentum. So on the first drop, as you might expect, the ice block shatters. So next up, we take some strips of newspaper and freeze them in about the same amount of water. And so here you again see the impact test. And as you can see, it has significantly higher fracture toughness, as it only makes a dent in the ice. The newspaper part is still intact. So we continue to do these impact tests until the composite material fails. After 5, we start to see some cracking in the material, and then after 10, we see some significant chunks taken out of the composite material, and then finally on the 11th test, the material shatters. The idea behind freezing carbonated water is that it would introduce air pockets and cavities into our material so that we can decrease our mass, but hopefully still retain some of the impact toughness that we saw in the previous material. The increased capacity you see here is an indicator that we've trapped more air. As one might expect, the material did not hold up to the fracture test, and so we include the paper strips. In a similar fashion to the other water and paper composite material, we repeatedly do the fracture test. And the only difference between this and the previous example is that after repeated blows, the material starts to fracture along the layers of paper. And so it's harder to determine if it ever actually fails, and eventually all it just becomes is the sheets of paper just separate. So I wanted to include material that is on one of the extremes of the spectrum in terms of mass. And so what this is frozen bubbles. So I mixed up soap and water and just took the bubbles and froze them. And so it is almost completely air, and it's very light. And of course, as you can expect, it has almost zero fracture toughness as itself. And then we can include the newspaper, and while that does hold together, all it does is just compress, and as you can see, it just flattens like a pancake, and it's not exactly very strong either, and so I consider that a failure. So I put together a little plot relating the number of impacts until failure versus the mass of each of these materials. And so as you can see, the paper strips in the ice or the seltzer were the strongest. There's a large error bar on the seltzer with paper strips because it started to separate in terms of the layers of newspaper, and so I couldn't really determine where it actually failed. The ice and paper strips had a definite failure right at 11 impacts. Everything else just failed on the first blow, so that didn't tell us a whole lot of it. But if we're trying to minimize mass and maximize fracture toughness, I'd say we'd probably need to go with something that displaces water better than strips of paper, but it's also stronger than pockets of air.
Two examples come to mind being wood chips and maybe certain kinds of plastic that are less dense than water.